let me start with fixing some notation and giving you guys some motivation and tell you what exactly we did and what I'm going to do today. Okay, so it's not good. Let R be a commutative domain with unit. If you guys want, you can just think about a field. So f is going to denote a non-constant harmonic polynomial in one variable. I sub f is going to denote the ideal generated by f. And I'm going to denote aught of I sub f, the group of automorphisms of I sub f, but I'm thinking about I sub f as an algebra without unit. Okay, so it's just linear transformations of IF into IF, which preserve the multiplication. And then Z of f is going to denote the set of zeros of f in the algebraic closure of the quotient field of R. So R is a domain. You can take the quotient field, and then you take the algebraic closure. All the roots are going to be there. Okay, so as I said, aught I sub f is going to be our main object and our goal in the paper. And this presentation is to describe the automorphism group of I sub f. Well, why would anyone try to do this? Well, I don't know why other people would, but the motivation that we had was the following. So if you have a finite dimensional simple Lie algebra defined over C, well, you can tensor this Lie algebra by polynomial ring one variable. This is a Lie algebra too. It's called the current algebra, and one can try to compute the second cohomology of G tensor C of T with coefficients in the irreducible finite dimensional module. Well, it turns out that the second cohomology is given by all the homomorphisms into the second cohomology of G tensor I, where I is the annihilator of this module here. This was proved in a paper by Brian Bowe, Chris Piaski, Dan Nakano, and myself. So what this result says is that the second cohomology of the current algebra depends basically on the second cohomology here. Oh, I'm sorry. This A, yeah. Thank you for pointing that. Yeah, this A is C of T. Yeah. Yeah. So in order to compute this side, you just have to compute this thing here. But we don't know how to do this in general. So we were trying to figure this out, and you need some tools to try to tackle this problem. And one of the tools that we were thinking about using was to use automorphisms of this Lie algebra here. But we didn't know what were the automorphisms of I, so I decided to compute the automorphisms of I. And so that's what I'm going to try to explain to you guys. Okay, so let me start with the main techniques, the main lemmas that we used. Try to give some ideas of the proofs. They're quite simple. So the first thing is, if you have an automorphism of the ideal, then there is a unique extension to an automorphisms of the whole polynomial ring. Okay, so this is basically commutative algebra. You kind of extend this automorphism to the field of fractions, and then you restrict and that's what it is. And then the second result is like, so on the one hand you can extend this automorphism to the polynomial ring, and on the other hand, if you start with the polynomial automorphisms of the polynomial ring, the restriction to I of f is going to actually preserve I of f if and only if it's just it just sends f to a multiple of itself. So these two lemmas are going to kind of guide the rest of the results. Okay, so let me give this. Let me give a definition, and you're gonna be able to see exactly why I'm going to define this. So I'm going to define gamma of f to be the subgroup of the permutation of the group of permutations of the zeros of f, such that, well, this permutation is kind of linear, and they preserve the multiplicity of roots. Well, the reason why when we define this is, well, there is an isomorphism between gamma of f and the automorphisms of I of f, I sub f. So the proof of this result is not hard either. I guess I can kind of give an idea of the proof here. So if you start with a sigma in gamma, then, well, sigma of z is is of this form for some alpha and beta, and then you assign to this sigma phi of sigma the maps t to alpha t plus beta, and then you restrict, and then you check that phi of sigma is going to preserve f, and then restrict this is going to be an element in the automorphism of phi of f. And on the other hand, if you have an automorphism of phi of f, as I said before in the other lemma, if you have an automorphism of f, there is an automorphism of the whole polynomial ring, such that when you restrict to I of f, this is our original automorphism. But the automorphisms of the polynomial ring, we know how they look like. So phi of t is alpha t plus beta, or some alpha and beta, and then you just assign sigma to be 1 over alpha z minus beta. That's what. So they're one is inverse of the other. So for this result, we highly use that we know all the automorphisms of the polynomial ring. But anyway, so there's an isomorphism, and the advantage, like what's the nice thing about this result is that you can kind of rewrite the automorphism of I of f in a kind of algebraic way, right? This gamma is kind of an algebraic group. It's a group with some geometric flavor to it, and that's what we are trying to do the whole time we're working on this project, trying to rewrite this into a more geometric way. Okay, so what are the main results? Well, the main results were, well, if f has only one root with maybe multiplicities, then the automorphism is just the units of this ring. Oh, this times here is just the units of the ring, of the domain. And this is just playing on that thing over there, so you can just use the alpha. The beta is going to be 0. If f has at least two roots, distinct roots, and this is a technical but important condition, and if the degree of f is kind of invertible in R, then the group of automorphisms of I sub f is a subgroup of the cyclic group of order degree of f minus degree of this root here. Sorry, minus z0 as a root of f. So it's a subgroup, but we would like to, and again, the proof of this theorem has the same flavor as the previous one, and just use the lemmas that I showed before. So as I said, this is a subgroup, but we would like to give a more precise description. We would like to tell, to know. So if you give me an f, I'd like to be able to tell you right away what is the order of this cyclic group. Okay, so the way you do this is, well, you decompose f by multiplicity of the roots. So if you have so z of f, you can take the subset of roots with multiplicity m for each m. Then you write f as a product of f1 times f2 squared times f4. Fm is going to be just the products of the t minus the roots that have multiplicity m. Okay, and then by those results that I showed before, there is an injective homomorphism of this alt of I sub f sub m inside of automorphisms of the polynomial ring variable, and then we show that there is actually an isomorphism group between the automorphisms of I sub f with the intersection of these automorphism groups here. So basically, what this term says is that you don't have to compute f in general. You can just restrict to polynomials with simple roots, and then to compute the automorphisms of polynomials with simple roots, all you have to do is go back to the previous lemmas and see what are the just compute gamma of f. What are the symmetries of your space that preserve the roots. So that's so basically what the corollary for this theorem is like. The order of this group is the greatest common divisor of the order of these groups here, and these polynomials have simple roots. That's all it says. And that was that's the furthest we can go. But then, well, instead of answering our questions, this result gave us more problems. And some of the things that we would like to investigate next are, well, first, we'd like to see what happens when the characteristics of R divides the degree of f. So this case is not taken care of in this theorem here. Because if the degree of f is divisible by the characteristic, then it's 0, and then it doesn't work. And actually, we have an explicit example where that theorem doesn't work, doesn't apply in this case. Then second, we would like to replace R, the polynomial ring, by a general algebra and compute the automorphisms of the ideals, of course, in terms of the automorphisms of A. This seems to be the most natural and interesting question that we can ask ourselves. And then, again, playing on that theme of trying to rewrite things in terms of some sort of geometric object, we came up with this variety determined by f. Let me try to explain what this thing is. Okay, so notice that I of f it's finitely generated as an R algebra by these elements here. So you can define homomorphisms of algebras like this. So you send unit to unit. Oh, and then enlarge I of I sub f with the unit, just to make this into a algebra with unit. And then define this homomorphism here. and compute the kernel. So the kernel is going to correspond to a certain finite subvariety of a to the d. D is the degree of f, and this is what we call the variety determined by f. And the question that we still don't know how to answer is, if given two polynomials, non-constant mnemonic, is it true that the I sub f and I sub g are isomorphic if and only if the varieties are isomorphic? And the most natural, actually, this question came about because we were trying to answer the question: is it true that the automorphisms of I sub f are the same as automorphisms of this variety here? So this is something that we'd like to answer, and it seems to have more geometric flavor, so maybe